Yep, all set.
Okay. I'll share my desktop and okay. All right. So, hey folks. So this is Johnny Rufus, and we are on Zookeeper Part 2. So in the last session, we actually saw an introduction to Zookeeper, right? So we'll probably have a quick 5-minute overview of what we saw, but the main goal for today's session is to keep it short and like just simply walk over a sample distributed kind of an application built using the CLI, and try to just see like how Zookeeper functions and stuff, right? So probably part 3 we can have it maybe not next week, but maybe a few weeks later, like once I think the DDA folks would cover consensus chapter maybe by 2 or 3 weeks, I believe. So once they finish covering the consensus chapter, then we can actually start looking at how does Zookeeper actually, the ZAP protocol, implement consensus, right? So pretty similar to, like how RAF does it, like using a quorum-based voting kind of a mechanism. Right. So, and so before we get into the sample application, so we kind of, so the last session, we actually started seeing as to what is a general problem with respect to, agreeing on something, like in a distributed system, right? Like, so what is exactly the distributed consensus issue? And like, it's mainly because of, like you have different things in the network and within the multiple nodes in the cluster that can actually go wrong. So because of which there is no single unified view, that can be kind of presented, like consistently, right? So that's where the consensus problems actually start creeping up. And like a very simple example is like you have let's say a set of data that's stored across more than one node in your cluster. So then, like what happens if when not all the nodes store the data, which is supposed to be present in the entire cluster, right? Like, so, some nodes are down, some nodes come back up. What if the order in which the updates are being made are actually not applied, like in the correct order across the different nodes, right? So in which case, like the data in these nodes can actually permanently, they can actually diverge, right? Like without any ways of reconciliation, right? So that's the essence of what consensus problem is. And we saw a lot of network unreliability, constantly coming up again and again, right? Like, so, and that's why even in the CAP theorem, like you can only choose between your C and A, right? Like, because you always assume that network partitions are, are unavoidable, right? So, and then I think this is the example application that we are going to see today. So, like where the goal is very simple. You have a single master. The application that you're building has a single master, right? It's a distributed application. It has a single master, and there are a set of workers that like that are available to do the work. And you can actually have a set of clients that submit the work to the master, so that the master can actually start assigning the work to the workers, and the workers can actually complete the work, and then like inform the either the master or the client or the worker stack, right? So how do we build this, like this distributed application using Zookeeper is what we are going to see today. And so yeah, so just as a recap, so we kind of saw that Zookeeper exposes a file system API, right? Like, so I mean, all operations that we are going to kind of see today, are going to be, related to how do you create files and directories within a normal file system. It's just the fact that you're communicating with a Zookeeper server, or not just probably a single server. You're communicating with an ensemble of servers in the Zookeeper cluster. And this file system is exactly what is being replicated across the different nodes in the Zookeeper ensemble, right? So so that's why, like these systems are actually called replicated state machines, right? So they replicate the state across more than one node in the cluster. Um, we also saw the API. So as I said, it's a simple file system. That's what Zookeeper kind of exposes to us, like as application builders, and like where you create a specific Z node. So each entity is actually called as a Z node, and you have a path to the Z node. There is an optional data that can be associated with the Z node, right? Like so, and then you have the file system API to create or delete, to check whether a specific path exists and stuff like that, right? And of course, because there is an optional data associated, you can actually set the data or even see what the data is associated to a given path, right? So we saw that. We also saw there are usually two kinds of nodes. There are actually three, right? Like so, one is the persistent ones, which get deleted only on an explicit delete command, right? Like so the ephemeral ones are more like, like as long as the session that created, right? Like so that specific ephemeral node exists, the ephemeral node will actually exist, right? So the moment that session gets terminated for whatever reason, maybe timed out or the client explicitly closed the session, then the ephemeral node actually goes up, right? So that's the concept of ephemeral nodes. And there are reasons why we would need an ephemeral node, right? Like so, like if you represent a worker by a Z node, right? Like, and if the worker currently is disconnected, like from a network, right? So then you don't want that worker to be represented as part of a state, right? Like so, it kind of makes sense to create the worker as an ephemeral node, right? So because the new worker that might actually come in the place of the worker that was dead probably may not be the exact same machine, right? So it could be a completely different worker. So we want to exactly reflect that. So we create ephemeral nodes for that. There are a few things like the task, like where a client could submit the task, right? But the client could get disconnected. That doesn't mean that the task should actually get away from the system, right? Because there will be a worker that executed the task, and probably there is a status available for the task, and the client could always come back and check the status of the task, right? So the task, when we represent the task as a Z node in the Zookeeper file system, we would represent it as a persistent node, Z node, right? And there is also the sequential Z nodes, like where we'll actually see in our example, like where you can actually, as and when you create more and more of these sequential Z nodes, like the Zookeeper system itself automatically keeps assigning incremental IDs to the Z nodes, right? Like let's say, for example, client one creates a task, like, and it's actually creating a sequential Z node. So it will be like task hyphen, and then the Zookeeper system would assign for the first one probably 000, right? So the next task that gets created by any other client would actually be task hyphen 001, and the next one would be task hyphen 002, right? So those are sequential Z nodes. We saw that, and then we also saw, yeah. So the one of the things that we kind of repeatedly, the problems with not just with respect to consensus, but when we build a distributed application, right? The master goes down. How do, like, if this application always has to have a master, right? And the master goes down. The question is like, like how do the other nodes or even the system, like come to know of the fact that the master is down, so that they can actually conduct an election among themselves to choose a new master, right? So there is this concept of watches we saw in the last session, which is kind of like setting a notification on to the Zookeeper server, saying that hey, I'm actually watching on the children of this particular Z node, or I'm watching on the data of this particular Z node, right? So you can set watches on both, and if something changes, right, let's say a new child gets created, or if the data associated with the Z node changes, then a notification trigger is actually triggered on the Zookeeper client, right? So and then we on the client we can actually take the action, right? So one thing that we might probably want to kind of take note of is, whenever I mean a Zookeeper client is basically an application, right? Like, so any application that communicates with the Zookeeper server has to use a Zookeeper client, right? So internally, a Zookeeper client is part of the Zookeeper, the part of the application that we are trying to build on top of the Zookeeper servers. All right, right. So we have this, and then what else did we see? We saw some, yeah, I think this is the general way, like as I said, right? Like, so each of these application processes, like the example, the master worker, right? Like your master is actually going to be an application process that uses Zookeeper client library. The worker is actually going to be even part of our own application, right? And also the clients that are submitting the task is also part of our application, right? So they all are going to use the Zookeeper client library in order to communicate with the Zookeeper ensemble. We saw that. And yeah, I think this is probably where we might want to start today, right? Like, so it's, hopefully we'll make this short. Um, let's see. Okay, so this is actually, so I have actually three directories. So ZK1, ZK2, and ZK3. So I'm basically, the idea is to like create a Zookeeper cluster of 3 nodes. Usually 3 nodes is a pretty heavily used like Zookeeper number of nodes in a Zookeeper ensemble. 3 or 5 is probably the most used Zookeeper cluster size, right? So and just to give what is there in the Zookeeper config, right? So I think for us the more important things are the client port. So the client port is where like we would want our Zookeeper client to actually connect, and then the servers, right? So like in Zookeeper, when we create a Zookeeper ensemble, right, a cluster of Zookeeper nodes, right? So the number of nodes is usually fixed, right? Like, so this particular configuration is static, it's kind of fixed. So what happens is when you start a Zookeeper server, right, you actually tell it where the other Zookeeper servers are, right? Like, so here we are saying that server.1. So server.1 is actually this particular ZK1, right? This particular server that we are kind of looking at right now, right? But you also say that there is one more server called server.2, like which is actually in the same local host, right? Because I'm kind of creating an ensemble of Zookeeper processes in the same node. But for all practical purposes, you could consider them as operating on 3 different nodes, right? And so the client port is different, right? So Zookeeper usually has 3 different ports. So one is the client port to which the clients communicate, and then the other 2 ports for each server, right? So one port is actually the quorum port, and then the other port is actually the leader election port, right? So they communicate. So for every right decision that the Zookeeper server makes, right? So it actually goes through this vote and proposal stage where like they have to get a majority quorum from the rest of the servers in the ensemble. And for that, they use the quorum port. And then they use a separate port for the leader election, right? So that's why you actually see 2 different ports mentioned for each of the servers, right? So, and this is kind of the same configuration. If you go to Zookeeper here, and then we actually see the conf slash right? So if you look at this, it's almost exactly the same. The only difference being, so because we are actually working in the same node, I made sure that like the client port is different, but the server 1, server 2, server 3, the IP address of the ports are exactly the same, right? So you kind of let your Zookeeper server exactly know what the ensemble is, and for this particular cluster, right? And the same thing for Zookeeper 3. Okay, so now let's actually see what happens like when we start the Zookeeper server, right? Okay, so yeah, so I'm going to use a Zookeeper server.shell command, and then I'm actually going to start this server. So the Zookeeper server started, and then let's see what the logs actually tell us, right? So the logs kind of, so right now there is only one Zookeeper server in the ensemble, right? So, and to even form a quorum and then elect a leader, right? Like, so it needs actually one more server to start, right? So that's why it's constantly kind of keeps pinging the other 2 servers that we actually gave, right? Like, so the other 2 local hosts and the ports, and it's not able to find those servers, right? Because we haven't started them yet. So let's see what happens when we start the other servers, right? So so I started this second server, and then let's look at the logs as well. So when I started the second server, right, so we actually see that the first server is able to kind of stop this constant pinging of the other servers, right? Because it's now able to find the second server, right? And among three servers, right? Because in the configuration, I just informed both these Zookeeper servers that there are three servers. But when you have three servers, for the quorum, you only need two of the nodes, right? And because two of these nodes are up, you actually see that they have actually finished the leader election process, right? Like, so inside the Zookeeper ensemble, they have finished the leader election process. And then if you guys actually look at the log for the server two, right? So the server two should actually be elected as the leader, right? So yeah, so if you guys, can you guys look at this specific thing over here? So it actually says that, like the peers has changed, and then this is the one that's leading, right? So the server two leads, and then the server one, um, you guys can actually see here, right? The server one actually started following, right? So usually there is one leader and then there are multiple followers, right? So, and the reason why, so usually, like when there are these multiple nodes that are kind of taking part in the leader election process, so they try to compare a couple of things, right? So each server has the latest Zookeeper transaction ID that it has processed, right? And it also has its own server ID. All right. So when you want to choose a new leader, you would actually choose the most latest kind of server, the server that has seen the most latest committed state, right? The one with the highest transaction ID. And in this case, right? So I think both server one and server two probably had transaction ID 0, right? So because they had not executed any transaction before this. So then usually what happens is the server with the highest number, right? In order to have a consistency as to to know which one gets selected, when there are multiple servers that have seen the latest transaction, so then the server with the highest ID gets selected as the leader. So that's why I was able to kind of like tell you guys, saying that what, server 2 should be the one that has to be the leader for sure, right? So because that's the algorithm that Zookeeper internally uses, because the transaction IDs for server 1 and server 2 probably was 0, and the server ID 2 is higher than server ID 1, so server ID 2 got elected, right? So now we actually know that server 2 is the leader, and then server 1 is actually the follower, right? So we can also start a server 3. Um, right. So, and you guys can actually see that, right? So it actually, the moment it actually started, it received the like who the new leaders was, and then it immediately started following, right? So the third Zookeeper server, it immediately started following the current leader, which is actually server 2, right? So now we have a Zookeeper ensemble of 3 servers, right? And then you have your server 1 and server 3 actually following, and then you have your server 2 in the leader state. Right, so this is the current state. All right, right. So let's actually start looking at, like, okay, we know that server 2, yeah, we kind of know that server 2 was the is the current leader, right? So why don't we do something? So let's just see, if I stop server 2, right? Because ideally, what's going to happen is when I stop server 2, which is actually the current leader within the Zookeeper ensemble, a leader election should again take place. And out of 1 and 3, I probably should see 3 as the leader, right? So let's actually, I mean, it also depends on whether 3 has seen the latest transaction, but let's look at that. So I actually stop it, and then okay. So when I go back to um, oh, sorry. I think I stopped the server 1, I guess, right? Okay. So let me start server 1. Let me move this a little bit down. Okay, this makes more sense. Okay, so let's right. So let's make sure that server 1 started correctly. Okay. Right. Yeah, server 1 is following, right? So server 1, we just stopped it and we restarted it, so it started following again. So I'm actually going to stop the leader, right? So when the leader stopped, and then we actually see that it actually lost the connection, and then we can actually see over here, right? So PS8 changed and then leading hyphen broadcast, right? So what happened was one, two, and three were there, and two was the leader, right? Like so, and then when I stopped the leader, which is two, then the leader election took place among one and three, right? And they probably have the same transaction IDs. So the one with the highest server ID gets elected. So you actually have server three as the current leader of the ensemble, and then we can actually see that the server one is actually just following it. And now if I start server two, it directly became followed, right? So now we just shifted the leader from server two to server three. Okay, cool, right? So I think so. Do you guys have any questions in this, right? So we have not even started building up our application, right? Like our distributed application. We're just simply trying to experiment with, within the Zookeeper ensemble, there is always a leader, right? Like and you always have followers, and we just saw that the leader election takes place every time the leader goes down, and then based on the transaction ID and the server ID, a new leader gets elected.
So, quick question: this leader election protocol and quorum, right? Are they just
Yeah.
they just used they're done using Paxos or?
Yeah, so they have their own version of consensus algorithm called ZAB, right? Zookeeper Atomic Broadcast,
Okay,
right? Like
okay,
so,
it's
yeah,
based on the Zap. Okay,
yeah, exactly. Which is almost very similar to Paxos, like in
got it.
concept, right? Like, yeah, yeah, or
Okay,
Raft.
got it. So basically, they build a Zap protocol, and then on top of that, they build this leader election and the quorums.
Exactly. Yes. The
Okay,
ZAP protocol is exactly used for those two things, right? So you have the quorum because for every right you need your proposal to be accepted by a majority. So you have the quorum,
correct,
and then
correct.
when the node goes down, the second one is you have to have a leader election, which is again has to be
Okay,
supported by a majority. So yes,
okay. I guess in Paxos, it doesn't assume anything underneath, so it's a different implementation. Got it.
I
Thanks.
mm.
Johnny, is it similar to total order broadcast, which DDI explains?
It is actually it is very similar. Like so, in fact, the ZAB actually expands to Zookeeper Atomic Broadcast. So,
Okay.
so that's the expansion for Zab, right? It is very similar to, I mean, it kind of implements total order broadcast internally,
So it
the
will
Zab.
send a message, and once all the nodes get a message. Uh,
Exactly. Yes.
okay. Okay.
It kind of guarantees the fact that, like in total auto broadcast, there are a couple of guarantees that we have, right? Like, so all, uh, all messages are delivered to all the servers in exactly same order, right? That's one thing. And there is also this termination condition, right? Like all messages are, for sure delivered, right? Like, so there is no they call it as a termination condition, right? Like so one of the requirements for total auto broadcast protocol, right? Like so Zookeeper internally the ZAB exactly does that.
Okay. Okay. So when the one node goes down, it is basically like the leader is not able to send a message, and that's how it identifies that one of the node goes down.
Right. So, so for all of these implementations, Zookeeper uses a majority quorum, right? Like so, so even if like when you have an ensemble of exactly three different servers, right? Like the setup that we have now. So if one node goes down, the Zookeeper quorum can actually proceed without any issues. Right,
Okay.
because it only needs a majority, like to even proceed with the leader election or to proceed with the like the voting process for any proposal that it makes, right? Like so as part of a right for any proposal that it makes, it just needs a majority. So right, so it'll broadcast those whatever proposal it actually broadcasts to all the other nodes in the system. If a node is down, the third node probably doesn't get it, right? But because the leader itself is one node, so it has its own vote always, and then as long as the other node is there, right? Like so the other node like we look at the proposal, and if it is in a consistent state, it will actually accept the proposal and it will actually acknowledge back, right? So the leader will actually have enough nodes to kind of commit the proposal.
Okay, okay. So what I was asking, like now, like we have a leader and two nodes,
Yeah.
everything is going fine, and suddenly one node goes down. So
Yeah.
is leader continuously polling every other node, or like how does a leader would know that one of the node goes down?
So I think internally they should have. So I don't know the details of exactly how Zookeeper keeps track of like what kind of pinging mechanism they have within the current set of nodes, right? So, but I think internally they kind of have watches on the actual Zookeeper state itself.
Okay, okay.
Right, like so the like we'll actually look at it. There is so Zookeeper itself maintains its own state inside a node called Zookeeper that is actually stores in the root directory, right? Like so so the way that I could think of is, like like how we are going to build the master application, where if the master goes down, they get a notification, right? So similarly, if a node goes down, the other Zookeeper servers will actually get a notification of the fact that a node went down, and because they have to know the fact, right? Like so, especially they have to know that if the one that went down is actually the leader. Right, like so because they have to start a leader election. Everyone will actually start their own leader election process, right? So but if the one that went down is actually a non-leader, right, like so it probably doesn't impact immediately, right? Like so if there is only one node going down, right, like they're okay with it, they'll try to send the message, whatever proposal, right? Like but because the node is down, it won't actually reach them. But where it'll affect them is, when they lose majority, right? Like so if two nodes go down, right, then and leader is still there, right? Like so when now the leader cannot actually proceed because like to write anything, it needs a majority, and it has lost its majority, right? I think, yeah, so they internally, the more important thing for them to keep track of is if the leader goes down, because they have to immediately start the leader election process.
Yes, makes sense. Thanks.
Okay, sorry. So okay, so we have this typical setup, like where we have these three nodes, and if you guys remember, so our leader is the Zookeeper server 3. All right, so let's start looking at how do we, like what happens when we start building the clients, right? So I have a different set. So we have so if you guys remember, the application that we are trying to build is a master, has one master node, and it has actually multiple worker nodes that can register saying I'm ready to do the work, and it probably has like multiple clients, right? So we are going to see a setup where we have one master and probably one worker and one client, right? Just for simplicity's sake, right? So okay, so I'm going to start the client over here. So it's actually saying that, let me here. Oh yeah, so okay, sorry. Yeah, so when I start the client, right? So one thing that that I have to, I thought it was in a config file, but yeah, so one thing that I have to specify to the client when I actually start it for the first time is I have to kind of let the client know like where the actual, what are the different servers in the ensemble are, right? Like, so here I'm letting Zookeeper client know, right? Like, so instead of doing it in a config file on the command line, I'm actually telling the Zookeeper client that the server is at the three different IP addresses, right? And then the three different client ports where the three servers are listening to right now, right? So when I do this, right, so we actually see that the client would have actually started a session, right? Like, so I just started a client 1. So the client started a session, and let's start the client 2. And there's a session 2 that gets started. Because if you guys remember from the last session, from the last discussion we had, like whenever a client starts its communication, right, like with the Zookeeper server, it always starts with a session, right? A session gets created, right? And the session becomes really important in the context of the ephemeral nodes and stuff, right? Because the ephemeral nodes lifetime is within the lifetime of a session, right? And even the right ordering is kind of preserved within a session and not across these sessions. So I started 3 different clients, and as I kind of mentioned, we are kind of building the application, right? So typically what I would do is, like I would actually not use the Zookeeper CLI, right? Like I'd be building using the Zookeeper API, and then I'll be building this, but just for the demo purposes, right? Like we are just using the Zookeeper CLI, and let's say the first one is actually where we are going to run the commands related to what the master is going to do, and let's say the next one is probably for the worker, and the third one is probably for the for the client, the actual client, like the client of our application who's going to submit a task, right? Like, so we have 3 different types of nodes that are going to be part of a distributed application, right? Like, so you guys have to like, I think even in the last session this came up, right? Like, so Zookeeper's cluster is different, right? Like, so and the leader in the Zookeeper is different, the followers are different, right? So what we are building, the master worker, is completely on top of the Zookeeper ensemble, right? Like, so these are completely different application processes that sit on top of the Zookeeper servers. All right, right. So, what is the very first thing that as a master, right? Like, so because we need to make sure that first of all, like one of the nodes actually have to become the master, right? Like, so right now we have three different clients, like, and the way to make sure that if you guys actually remember in the last one, we kind of saw a very simple um, um, a very simple way to create a master and make sure that there is only one master, right? Like, so if all I have to like create is if I create a slash master z node, right? Like, so and like, let's say like you have like, you start up your system and all nodes are kind of equal until one node becomes a master, right? So all nodes try to execute this command to create the master, and because Zookeeper provides you the integrity, only one of them, right, will be able to create the z node called slash master. So which means that node that actually was able to successfully create it would be the one that actually becomes a master, right? So in this case, we have three different clients. Let's see what happens. So I have to, so let's actually do ls slash just to make sure that, okay, so I just have, so in the root of my file system, I simply have a Zookeeper directory, which is used internally by the Zookeeper. So let's not worry about this. Let's create a master. So create, and then -e stands for ephemeral, right? Like, because we want the master to be an ephemeral node, right? Because if the master goes down, right, like we want the z node to actually go down, and we want the notifications to be triggered for whoever else is kind of watching, right? Like, so and all the backups who are watching that can potentially become masters, they need to know that the master goes down, right? So that's why we create it as an ephemeral node. And yeah, so the path that we want to create is just slash master. And we probably can like in a master, typically like, what do you kind of data that you want to put it, this could be anything, right? Like, I can simply say some xyz colon like 1000 port, like as the port, right? So whatever like you want your masters exposed IP address and port is, right? So create it, and then it actually says created slash master, right? So now the thing is, so if I simply go back to my client 2, right, and then I try to create the master, it basically tells me that the node already exists, right? So one of the nodes, right, let's say we have multiple nodes in the system, one of the nodes that executes, that successfully, the first one that successfully executes this create command, right, or calls an API in an actual system, would be able to become the master by being able to create the slash master z node, right? And we see that it's an uh, ephemeral node, right? Um, and then as I said, right, so when you have all these multiple different clients, right, so we have this master, and the one thing that we have to immediately do is, all the ones that fail to become masters, right, so they need to kind of know that the master, like, they need to kind of have a watch on the master. You guys agree to that, right? Because otherwise, if the master goes down, your application is masterless, right? So one of the other nodes, that can potentially be, like any of these workers can become a master, right? Like, so one of the other nodes can actually become a master, right? Like, so you want these nodes to set a watch on the master. And how do you actually do that is, if you guys remember from the last session, if you execute any read command, right, like you any read command is where you kind of give the option to set a watch simultaneously, right? Like, so in this case, like, let's say we actually do the stat, and then -w, and then slash master. All right, so you want to kind of like look at the stat for the master, but you're also giving the -w option to make sure that you're kind of setting a watch on the master. Right. So currently it kind of gives you a lot of information about the master, like the number of children the master has and stuff like that, whatever that slash master z node is, right? And it has also set the watch, right? So can we check the watch, right? So because I can simply like because this is a client, so, and this is my master client, right? So this is the So I simply kill this session. I'm still waiting for uh, the watch to actually happen. And for some reason, my -w didn't set the watch, right? Okay, so there are a couple of things that changed. So let me go back to this. And then, create, actually, if you guys now look at ls slash, right? You don't have master anymore, right? We didn't delete the master, but what happened was we killed the master, right? Like we killed the client that created the master. Because master was an ephemeral node, the master also disappeared along with it, right? So let's just see some, yeah, actually we can see the watch. So it sometimes it takes a little bit of time to actually get the watch. So you guys can actually see that, right? Like, so we kill the master, and then because we set the watch over here using the stat -w, right? Like, which is actually read on the Z node, but the -w sets the watch. So you guys actually can see that, like there is a watcher event that happened, right? That basically said, like the slash master got deleted, right? And probably one of the reasons why it kind of takes time for the watch to get kind of triggered on this particular node is because usually when the session goes off, right? So there is this session timeout for which the Zookeeper server waits until it actually declares the session dead, right? Like, so it waits out the timeout, then it goes and deletes that all the ephemeral nodes associated with the session, right? Like, so, and then it actually triggers, and the deletion of that is what kind of triggered the watch over here. Probably that's the reason why it took a little bit of time for us to see this, right? So yeah,
Right now the application is still masterless, right? It was just notified that the master node was
went down.
deleted,
Yes, yes,
but the
yes.
master
So
is still not there.
yes, exactly. So right. So as I said, so I'm right now I'm actually writing the application on the CLI. Right. So ideally, if this was a program, right, like, so what would have happened is, like on the whatever callback that got executed, like for my watch, right, like whatever listener that got executed for the watch, right, so that particular callback will actually start a create -e/master command in order to create a new master. So yeah, right. Like, so in the CLA, for example, right. So what would have happened is, like, okay, fine. So now that we got this watch, so what would node 2 do in the API, right? So the node 2 would actually try to do this, right? Because it got the watch saying that, like the callback for, like, okay, like, try creating master would be executed, right? So then this would actually do this, right? And then it would actually probably saying, what, this is client 2 dot x dot y equal 1000, so some data related to wherever this guy is supposed to listen to, and then it does, and then it's able to create the master. Yep. So in the API, right, like when we write this, instead of this being a CLA, right, if this was an application, that this is what the callback would have done. Like, so you had a master, the master went down, there was one node that was watching for it, the node got notified, and then as soon as part of the notification, like as part of the callback, like the code for this specific callback, right, like, because master down would be to create a new master, right? Try creating a new master, because we don't know, right? There could be multiple nodes watching, and all of these
Yep.
nodes would have gotten a callback, and only one of them would succeed. Yeah.
And would any of the workers would want to know who is the master among them, or does it not matter?
Right. So yeah, like, we actually kind of, like, when we created this master, right? So one of the reasons we kind of we put the information saying client2.xy, like anyone who needs to know where the master is kind of listening to, right? Like, so they can actually
Hmm.
read it from there, right? But in our current application, the way we are kind of going to submit is, the worker need not actually know this information. The worker has a way of directly interacting with the Zookeeper to kind of let the master know that, like, that it is available, right? Like, but yes, like, if the worker wants to know who the master is, the worker can always do a stat/master, and it should be able to see the contents of whatever that master Z node is, which is probably where the master, whoever the master is currently, right, like, would be actually listening on that server and IP address. Yeah. multiple different ways. So we are the way we are trying to going to build is, like where the worker, in order to how does, I think the next thing that we are going to do is exactly that, right? Like how does the worker, so right now we just talked about the master, and we saw that, like the master goes down, the notification gets triggered, someone else becomes the master. So right now CLI2 is basically the master, right? So the next step, right, like, so okay, we have master, we know the failover for the master. So the next step is actually, we'll see how this whole task system can be implemented in one way, right? Like there are different ways we could do this, but like one way of like making sure that this application actually works, we would probably be looking at today, right? So okay, so now that we have this master, what is the next thing that we actually should do, right? Like, so we should actually so let's actually take a look, right? So we need workers, all right? So and we also need tasks, and then we also need to know the assignment of which worker to which task, right? Like, so and we are going to use Zookeeper extensively to actually achieve all these different things, right? So let's actually start creating these nodes, right? Like, so because as I said, like the way we are going to write this application is such that, like they are not going to directly communicate with these masters or servers. Like everyone knows Zookeeper, right? Like, so everyone knows the file system of the Zookeeper, so everyone is going to record their information in the Zookeeper, and all the other interested parties would be able to kind of execute this whole application just by by creating the Zookeeper, creating Z nodes in the Zookeeper file system, and getting and setting notifications and watches, right? So that's the goal for today. So we have to create a all right, so we have to create a slash workers, right? So this is where the workers are going to register, right? And probably, like no data associated. So we created workers, and then probably slash tasks, right? And then we also create a slash assign, right? So we'll actually see exactly how these nodes are implemented. So if you guys actually see, right? So there's a difference when we never gave this hyphen E, because the slash workers is actually the root of all the workers. When we create a worker, right, we'll actually create it as an ephemeral node. But the slash workers is basically in a way the master will kind of like start looking for workers, right? If at all it needs to find a worker, right? Like, so, and then the task is exactly the same, and then this assign is where the both the master will because as I said, because in this particular example, the masters and the workers and you and the client, they are not going to communicate directly through each other, right? Like, so which is how I think normally it would happen. But in this case, they're just going to communicate using using this shared Zookeeper file system, right? Like, as you guys kind of like broadly, there are two different ways of communication, right? Like, one is message passing, and the other one is using shared memory, right? Like, so either you have IPC. All IPCs can either be done by message passing, or they can done by shared memory, right? Like for simple, you can simply like start using a database, and then and write the information, and whoever the master is, for example, like starts maybe constantly keeps polling the slash task table, and whenever the client puts a task over there, the master kind of like in one of its polling, it'll be able to see that a new task was there, right? We are kind of using right now we are kind of using that shared memory kind of architecture, where everyone communicates with each other by using that shared file system, which is our Zookeeper. Right? So we have these three different. So let's actually see in a root. So we actually have assign. We have the master. We have the tasks. We have the workers, and then we have the internal Zookeeper Zeno. Right. So these are the current system.
So quick question here.
Yeah.
So these slash workers slash task slash assign, right? So these like the shared directives can be created only by a master, correct? Only a master can create this, or anybody can create this.
Actually, anybody can create this, but the workflow would be such that the master is the one who would create it.
Okay.
Right. Like, so this can actually be executed, because I mean there is no like, so I mean like the like if you guys actually look at it, right? So like from the perspective of the Zookeeper system, in all the three clients are kind of same.
Right. Anybody can try to create, and whoever gets try to create first will get that permission. Like if they will create, right? Others will fail.
Yeah, probably. But
yeah.
Yes, but probably when we write it as an application, the way we would write it is whoever assumes the role of the master would be the one who would immediately create it if it doesn't exist. Yes.
Got it. Understood. Thanks.
Okay, so we have these workers and tasks and assigned, right? So one of the first things in, let's say, okay, the next thing is, okay, we have the master, right? So next, we have to introduce the workers into the system, right? And as I said, all kinds of communication in the system is going to happen through the file system, right? It's like writing something into the database, right? So the worker is going to come and register. But even before we probably do that, right? Like, so, like the master should be aware of, like two different things. If you guys kind of closely look at it, right? Whenever a worker registers itself, the master should be aware of that particular fact, right? Like, because the master, could have a task pending, and it's actually waiting for, like some worker to become available, right? Or a new worker to come into picture, right? So the master should actually set a watch on the slash workers and then the slash tasks. And that's exactly what we are trying to do, right? So we can actually say, like if I can simply do the ls-w and then say slash workers, right? Like, so right now it's empty because no worker has registered it, but we have set a watch. So let's say, because this the second is the master, so he sets a watch, and then we also set a watch on the slash assign, sorry, slash tasks, right? So we have set a watch on these two things. And okay, right. So now we can actually allow the worker to proceed, right? So what I'm going to do is, like, let's say maybe let's look at the first one. Maybe let's use this as a worker. I mean, like, as you guys understand, like I could execute this in from any of the clients, right? So I'm just trying to separate, okay, what the master does and then what the worker does, because that's how, when we build the application, that's how the workflow is going to be, right? So let's say we have create, and then and again, so here, because as I said, like when a worker goes down, like we don't want that worker to be available, because if the worker node is still there, the master would probably start assigning something to that worker, right? So we want that worker z node to get deleted when the worker goes down, and that's why we are kind of going to create it as an ephemeral one. And then it's actually going to be under slash worker slash, probably we can say it as worker one. All right, so slash worker one, and maybe we can actually have something like worker one dot like whatever abc.com, some information with respect to some communication information for the worker, right? So some port over here. And so this is just the like, so right now, when I execute this command, all that's happening is, a worker node like came into the cluster, and it's kind of registering itself to the system saying that I'm available to do the work, right? So we created this, and probably we see the watch, or the place where we kind of set the in the session, basically the session that set the session is master session, right? So we said on ls-w slash workers, which means if any of the any new children gets created on this slash workers, let me know. And that's what happened over here. We created a new worker over here, and immediately the master knows about it, right? So probably the master kind of know, like has its own I mean, when we write it as a program, the master has its own list of workers, like that it maintains, so that like when a new task comes into the picture, it's probably be able to look at its list and then assign something to it, right? So whatever the master has to do over here through the API, the master will do. But it got the watch, right, for which is actually set. And as you guys kind of know, usually the watches are always one time. Right. So you remember we actually saw this in the last session, right? So if we still want to kind of reset that watch, right? Like if we want to get notification, so usually the way is, like I get a watch, the watch actually goes off from the server. So the next time I do another read, and then I actually set a watch, right? So I just set the watch. All right, right. So this is done. So now that we have one worker node that is registered, right? So what is the next thing that we have to do? So we have the master, we have the worker, we have we go for the client, right? So the client is basically someone who creates a task, right? Like, so it could be any task. So and we can actually create. So for the client, so because the client is going to create the task, right? So, and we want to see the task, like kind of numbered as task one, task two, task three. We actually create it as a sequential node. So, and it creates it under slash task hyphen. All right, and maybe whatever. So usually, the client creates it. It kind of gives some like some executable information over here, right? Because I mean, it's kind of creating a task, right? So whatever data it has, it's probably pointing to some executable that needs to be executed as part of the task, right? So we are creating a okay, so Zookeeper just created the task hyphen, and because it's a sequential, we just gave it task hyphen, right? So it created the first sequential node under this slash tasks is always hyphen 00000. So it actually got created, and probably we saw another watch that got triggered on the master, right? Because there's a new task, right? So this so in the previous worker scenario, the master simply probably noted the fact that there was a new worker, right? But it's exactly when the task comes into picture, the master has to do immediately something, right? Because there's a new task that was actually submitted to my system by the client, right? So ideally, like in an API, when we write this application, like when this particular new task got triggered, what would we have to do? Right? Like, so we would actually do some kind of an assignment, right? Because we know that a new task existed. I'll probably, like start reading what the slash task is. I see that there's a task hyphen 0000. So which means that I know that there is a task. And how do I actually assign this? How do I actually assign this task, right? So even before I assign this task, right? Like, so this is from the master. So the worker should actually have done something, right? Like, so the worker should have let's set a watch on. So what do we have here? So we have ls. Sorry. So we have because the worker should know the fact that the master assigned to it something, right? So how does the worker know that? Okay, so the worker would actually the worker would create a ephemeral node, right? Like, so because yeah, so if you guys actually think about it, right? Like, so the worker registered itself, so that is one thing, but the worker should also kind of create a node under the slash sign, so that, and then start watching it, right? So that when the master assigns it somewhere, the master will create a sub node under the directory that I'm going to create. And because I am watching it, I know that the master actually has assigned me some task, right? So I have to create this slash assign slash worker one, right? So assign slash worker one, and probably just and this has to be an ephemeral node, right? Like, because it has to exist as long as this worker is there, right? So I created this, and then I also set a watch on this. Right. So by doing this, I actually set a watch on this particular whatever, like so now whatever will be assigned to me, I'll be able to like get a notification, right? And now that, okay, so this is some pre-information that we should have done immediately as soon as we created the worker one, right? So the worker one registers itself, by creating a node for it under the slash workers, but at the same time, right? Like, so it also registers itself under the slash assign, right? So that the master can assign it something, right? So now the master, right, like, so got a task, right? So when it got the task, it actually looks at slash workers, probably does something like that, and it knows that there's a worker, right? So what it does, so it actually it has to assign, right, like a task. So it's going to create, right? So as I said, like all communication is going to happen by modifying this file system, right? Like, so the master is going to create what do you guys actually think, right? So should the master create an ephemeral node, or should the master create a persistent node under the under the slash assign?
Ephemeral one.
I think it should create the permanent one, right? Because that way, if the worker one goes down for some reason,
yes,
there would be at least an entry saying that something was assigned to worker one. Worker one is no more there. So now do some sort of reassignment.
Exactly, right? Like, you guys get the reason as to why we need this, right? Like, so if we create an ephemeral, right, because it kind of looks like we might need just an ephemeral over there, but the only place where the information as to the fact that, whatever this particular worker one was doing is actually is going to be under the slash assign kind of directory, right? Like, so for the worker one, right? So whenever the master gets a notification that the worker one went down, like, how does the master know what task to look for, right? What task to restart, right? Like, so then we have to create a permanent one, right? So I'm going to create a slash assign, right? Like, so assign, and then I just saw that there's a worker one. So I inside the worker one, I'm actually yeah. So the way I'm going to do it is like so I have a slash assign, and then so within the worker one, I can simply create a task, right? Like, so whatever the whatever this,
Okay,
right? So whatever
Johnny,
the
I have a
task,
question
yeah,
here.
yeah, sure.
So we have this task right now, like for worker one.
Mhm.
Now worker one is down, so we don't have node at worker/worker/worker one. Then we got a new one. How will you create another assigned task like slash assign slash worker two slash with the same task?
Exactly. Yes. So because you are, so this is a very simplified system, right? Like, we are not kind of like, let's assume that, like in this particular system, right, there is no checkpointing of the stuff. And if the worker that actually fails, the worker that's executing this task, right, let's say it failed, and if the master kind of goes and tries to check the status of that, and it sees that the
Mhm.
status is still not yet done, then the goal of our system is, make sure that we kind of assign this task to a different worker. And it's exactly like you mentioned, right? Like, I'll actually go and actually look at slash assign slash worker two, and then I actually create whatever this task -00, right? And create this under that slash worker two, because that slash worker two would the worker two would be listening to that slash assign slash worker two Zeno, right? So the moment
Mhm.
I create this same task -000 there, it would actually get notified, and then it will start executing the task.
Who will clean up the stale record then?
The stale record for the fact, okay, the fact that the master should be able to take care of it.
Okay, yeah.
Right, because the master is the authority over here, right? The master kind of knows the state of the system, and the master is the one that got notified of the fact that the worker went down. So because of that, the master would immediately not just like all the cleanup, right? Like, so assigning that work to someone else is part of the cleanup. Also deleting, whatever that the previous assigned for that particular master is, for that particular worker is also part of the master.
So, but once the worker
Yeah.
finishes a task, right, it just removes that path file, correct? Node, correct?
Right.
So
there
let's
are
say task 0,
yes.
task 0000. Once master assigns to worker one in that path, right, using that file name task 000.
Yeah.
And once the worker one gets notified through the watch and it knows it's a task, it reads the task and finishes the task. After finishing it, it will just delete that file, correct?
Probably yes, right? There are a couple of ways we can implement this, right? So one, either the worker itself, like finishes the task, and then it notifies either the client or the master that the task is done, and the worker itself can either delete it, or like once the master gets the notification of the fact that the task was done, the master can delete.
Got it. And if the worker dies, the way master knows is basically that worker slash worker slash that worker one will disappear. That's how the master knows, right? To the watch.
Exactly, because the master has already set a watch on that slash workers, and when worker two, let's say, goes down, that Z node gets automatically deleted because it's an ephemeral one, and then the master will get notified.
Got it. Thanks.
I have one more question here.
Sure.
So we want this particular uh, path to be permanent, but I think assign slash worker one was ephemeral node itself. And if we are trying to create non-ephemeral node inside an ephemeral node, I don't know what happens.
Actually, let's execute it and see. Right? Probably it won't allow me to do that. Exactly. Okay. Thanks for the. Okay. Yes. So okay. So in this case, because the worker one itself was ephemeral, right? So which means that I can't create a non-ephemeral one under the ephemeral one, right? So let's actually see how does master know what was the task that was handled by worker one. All right. So maybe we should have created the slash assign slash worker one itself as actually a permanent node in that case, rather than
Or
ephemeral.
what we can do is that like a lot of ways, but what I was thinking is that workers slash worker one, that is an ephemeral node itself. So maybe we can create some file there, and also here to keep the bookkeeping that this task was assigned to this particular worker in the permanent manner under the assign folder, and all the assignments for each worker under its own ephemeral node, something like that.
Sure, I think even that works. There has to be somewhere where it is non-ephemeral, right? Like so that that
Yeah.
information is kind of retained. So at some point it has to be. So in this case, right? I think the right. I mean, not the right, but one way where like the some point where we want to kind of store it, even if the worker goes down, is probably if I because in the slash worker one, if I had created that as a permanent node instead of an ephemeral node, right? Then I would be able to store the task information directly under that, like as a permanent node. So the master can, because for the master, because when worker one goes down, what does the master need to find, right? It needs to find what are all the different work that was assigned to worker one currently, right? So for that, if it simply has to look at slash assign slash worker one.
Yep. And we always want workers slash worker one to be an ephemeral. That is our direct way of notifying to the master that worker one died.
Exactly.
So
Yes,
that
that has
needs
to
to
be
be
ephemeral
ephemeral
for
for
sure.
sure. Yeah.
For sure. Yes. So in this case, right, so let me go back and see. So this is actually slash assign slash worker one, right? So I need to let's say slash assign slash worker one. Okay, so that's empty. So which means I can actually remove it. So so what is the command? Is it delete or remove? It's actually delete, right? So I can say okay, delete slash assign slash worker one. Okay, so that got deleted. So now I can actually create it as a non-ephemeral slash worker one. So that's a non-ephemeral one. So now if I go back and start executing this in a like worker one task I want 0, so that got created. Yeah. I think the key is like yes. So as you said, right, like we can create this directory structure in multiple different ways, but as long as we have one path, right, where we store this assignment and that doesn't get deleted even when worker one is deleted, right? Like the master should be able to refer to that path to figure out what the outstanding tasks are and stuff. Right. So we created this task, and then we created it under slash assign slash worker one, and yes. So on worker one, we actually got a notification saying that there is a task that was assigned, right? Like because as you guys remember, so we actually had this ls-w on that slash assign slash worker one, right? So now the worker one knows what the task is, right? So if it does this,
Hold on, this one is for the delete. The task
Correct. I think
assignment
it
is
might
not
not.
there yet.
Mhm.
which one? Oh,
This
so
notification is for the file with the node which we deleted, right? Because it was ephemeral.
okay, so okay, so then okay, let's look at this. So so before we when the idea is like when the task gets created, right? So I should be able to see that in the worker, right? So let's actually delete it
I
again
think we
here.
need to have watch again there in
Exactly,
master.
we need to set the watch. So I'll first delete
Mhm.
this, right? So that when I create it, the watch gets triggered, right? So now I actually have to because the deletion I think already triggered the watch. So I will not actually get the watch again because we didn't set it again, right? So now let me set the watch again, and then I set the watch again. So the watch is set now. So now if when I go and create this, right? So I got the watch. Right? That actually says no children changed and the path is slash action slash worker one. Yeah, thanks for pointing that out. I didn't realize the delete would have triggered that watch, right? So yeah, because it's a kind of watching the children of that worker one, right? So when we deleted it, it set the watch, but now I think it's on the correct track, right? Like so we created the task and then we actually the worker one kind of knows that there's a task. It probably reads what the task is, right? So and then it should be able to, like, so yeah, so the typical workflow of this particular worker would be, like, okay, it knows that there is a task assigned, it goes and reads whatever that Z node is, right? Like, so under worker 1 and under task 00. So, and then it actually figures out what the command is, it executes it, right? So the final question is, how does like, let's say for example, the worker finishes the task, the worker doesn't probably have to communicate to the master, it simply communicates to the client the fact that, like, the task got done, right? So how does the client actually know of the fact that the task got done, right? So what the client can actually do is, because the client created this task hyphen 00, right? So the client can do something like this, right? It can actually set a watch on the task hyphen 00, right? So by doing this, so the client has actually set a watch because the client just submitted a task, right? So, and then it sees that the submitted task ID is task hyphen 00, and immediately to know of any like whatever the task, right? Like irrespective of who is handling it or whatever it is, the client simply needs to know that that particular task is done or something, right? So it basically sets a watch over that slash task, and then this thing, and then what the worker is actually going to do once it finishes, right? So let's say the worker completed the execution of the task over here, it finished. So the worker is going to create a slash status node, and then it's going to say done. Right. So, and then actually, sorry. So the client, because the client kind of, like the client is kind of launching on the status of whatever, right? Like, so whatever gets created, maybe, the status was, like failed or whatever, right? So whatever the worker realized at the end of its execution of the task, it basically goes and creates a status node. And then the client can now actually simply look at, what this, right? So it looks at there's a status, and then status, so why is it not right? Like, so
Is stat on that you are doing,
yeah,
Alice?
probably, yeah, exactly. So let's do the stat on that. Yeah. That should give me at least the information on that, right? Status, and then even then it's not able to see. Is it able? Can you guys see the done over here? No. Did I actually? Yeah. So I set the status, and then I actually set the value to done. So how do I actually look at get, right? So yeah, so when I do a get, so I'm able to see what the data for that particular status is, and then you should be able to see that it's actually done.
So, but when that value changes, also it gets notified to watchers, correct? That's how
Yes,
value.
yeah, yes, provided the client, the client actually sets a watch
correct.
on that.
Okay.
Yes.
Got it.
This may be outside the scope of the discussion, but I still want to ask it. What if the worker 1 picked up the task, completed that, but failed before writing it as completed?
Right.
What happens in such cases?
Yeah, right. So as I think as I kind of initially mentioned, right? So like right now we are simply building the fact that, like, hey, these tasks are probably idempotent. So, like if the worker finishes it, but it failed to write the status of it, then we simply have to, rely on whatever status the worker created, in which case the worker never created the status. So we have to assume the verse saying that, the worker never executed it, and we'll probably have to redo it, right? But when we actually build a real worker kind of system, if we build it using Zookeeper, then, we'll have to, we'll have to kind of handle it in different ways where, probably there is a constant checkpointing that happened, and it's like the worker finished the task, right? So, but if the worker is not, if the worker failed before it could write the fact that it could convey the fact that it finished, probably there is not much that can be done, right? Like, so,
yeah, I think that semantically it's called exactly one semantics, right? So I think that's very hard to achieve.
Right.
I think the only way is if the operations are idempotent, meaning like you do once, even if you do multiple times, there's no side effect, right? So
Yep.
that will be fine. But otherwise, I think achieving exactly once, right, is very tough.
Yep.
There is no way to guarantee, I think.
I agree, right? So maybe the worker, the task, like if the tasks got successfully completed, there is some, there is some output file that it probably created. So we can probably go and check depending upon what that particular task was. There are other few things but not directly through Zookeeper, right? Because here we kind of depend on the fact that, like the worker fails, then, and it has not communicated its status. We can't assume anything on the status.
Yep, makes sense. Yeah, incremental checkpointing would be a better one, that is task picked up, maybe processed 10%, 15%, something like that.
Exactly,
That would
right?
really help.
Yeah. I think that's what happens in like even in, for example, right? Let's say let's look at a typical system. Let's look at MapReduce systems, right? So even in the MapReduce systems, like when one of the so let me think, right? So when one of the mapper fails, right? Like, so usually when a mapper fails, the mapper is completely restarted, right? Like, and I think that's the same case with the reducer also, right? Like, so because if the mapper fails, the problem is the output of the mapper is returned to a mapper's local file system, right? Like, so which is still part of the HDFS, but still it's kind of it's local to its own local file. So every day, whenever a master fails, the MR system simply restarts whatever that particular mapper was supposed to do. Like whatever portion of the data the mapper has to work on, there's a new mapper that actually starts working on it, right? Like, so it doesn't kind of checkpoint, but that's a batch system. So I think it has that time.
Yeah, I think in that example, right, typically they're, because they're batch system, they're idempotent. You just like maybe just duplicate, you end up duplicating it, but it doesn't really cause any side effects. But things like, let's say your task is send an email, right? You may send, but just before writing the status, right, you crash, right? But the email already sent, right? That's not important. If you try to send again, next time it will go again.
Exactly.
Right? So that's a difficult example.
I agree. I think usually so one of the things that like that they try to use is if there is a support for something called as an idempotent key. Right, like, so like if let's say I'm sending an email through a third-party service that accepts this idempotent key, right? Like, so usually they use it for payment services, right? So like we submit a payment, and then and then the payment service maybe process. I mean, there are multiple failures points, right? Like, so you submitted it, the payment service failed when processing it, or it processed it, and then the acknowledgement, the reply didn't reach back the node because of a network partition or whatever, right? So whatever reason, like me as an application submitted a payment request, I never got back a reply, and I have no clue as to know whether the payment got processed or not, right? So then if I resubmit this payment, like the card could be, the card could have been credited twice, right? So then, like, I think in that scenarios, the payment service usually provides something called as an idempotent key, which is like a transaction ID. So when I resubmit it, I would submit it with the same transaction ID, and the payment service kind of takes care of the fact that it will look at like it guarantees like maximum once daily execution of the API calls, right? So when it looks at the transaction ID, it knows internally whether it executed it the last time or not, right? So maybe it executed successfully, in which case it doesn't execute it, but it simply says a reply of done because it had already executed it, right? So I'm just saying another way of, as you mentioned, idempotency is very hard to guarantee unless the service that we are using gives us some way of figuring it out.
Makes sense. Thank you.
I think so we kind of saw the whole process, right? Like, so even though we just use the CLI, so we kind of saw the whole process of like we initially created this whole set of ensembles, right? Like, so 3 servers, and like the leader election taking place, the master going down and stuff, and then we also started seeing like, okay, how do I implement these these masters, workers, and clients, right? Like, so we open 3 different sessions, and then, like the master created its all the different paths, and then the workers registered. The workers also registered under /assign, and started watching it. And then the client kind of created under /task. The master was watching it, so the master woke up, looked at the task. It reads what the list of workers are, like does some kind of load balancing, or randomly chooses a worker, and then writes that particular information under the /assign path. And the worker actually, let's say it writes to worker one. The worker one is actually listening to that /option/worker one, because of which, it gets notified of the fact that it has a new task to take care of. It looks at it, figures it out, executes it, completes it, and then it actually has to notify the client. So the client actually, since it submitted the task hyphen that particular task under /tasks, the client is kind of watching that particular task. So when the worker finishes it, it creates a status node under that particular task, and then puts what the status is, and the client kind of gets back. It gets a notification, it looks at the status, and it gets it done. Right, so kind of a very, very simplified, how does, I kind of like this. So this example is taken from the book, right? So the book kind of exactly does what I did over here. So it's that Zookeeper, the Art of Building Distributed Systems. It's the O'Reilly book, right? So they basically detail the whole thing that we did over here. But I really like this application because it's a toy application, but usually we always consider message passing, right? Like, so all these things would have been RPC calls, right? Like the master, assigning something to the worker would have been like an async call to the worker saying, okay, fine. The worker exposes a set of APIs, the master calls one of those, and then, and then it assigns. Right? Like, so, but here we are looking at a different paradigm, which is actually kind of a shared memory architecture, right? Like, so, where the changes to the shared memory is the way through which all these different nodes in the system communicate with each other to to um, uh, to to fulfill the application requirements. Any other question, guys? I think that's all I have for today.
I have one more question about the behind the scenes, the Zookeeper instance. There are 3 servers which we have started here, right? For the Zookeeper. I think two were started. I forgot how many are there.
Actually 3. We have all 3.
So it is possible that all these 3 client applications, the CLI basically, they might be talking to any of them. Is it possible, or are they only so for the read operations? Maybe for the write, the CLI may be choosing to write to the master, but for the reads, can they go to, or are they going to any of the 3 Zookeeper servers?
Yes. So the fact that if you remember, in fact, even when I tried creating the Zookeeper client, I actually didn't give the ensembler service to it, right? So we literally tell them, but we don't tell them who the master is, right? Because that information is a fleeting information, right? Like, so the client usually is not aware of who the master is, right? Like, so the client simply connects to one server in the ensemble who's currently working, right? So and so internally the client does that, right? And it establishes the session, and it can actually read and write from that particular Zookeeper server, whatever it is, either a leader or a follower, right? Like, so in terms of the Zookeeper ensemble, we call them a leader and follower, right? So and if it's a follower, if it's a read, the client basically, the follower literally executes the read, and then it gives the information, right? But if it's a write, the follower always forwards it to the leader, and then the leader actually does a quorum proposal, voting thing, and all those things, gets a majority before it propagates it. Yeah, it does. It basically executes that atomic broadcast protocol.
I see. I was thinking maybe the CLI is smart enough to identify who is the master and then forward. But this makes more sense that each CLI is talking to one server, one Zookeeper server, and then that does the job of forwarding to the master if that server is not master.
I
Makes
believe so.
sense.
Yes. We can probably double check this, but as far as I remember, I think the client usually doesn't get exposed to who the leader currently is. So it simply establishes connection to one of the servers, and then it simply talks. So it always has its session. I think now I think I can even confirm the fact that it's just one server, right? Because it establishes the session with one server, right? Like, and it doesn't communicate anything other than that established session to whatever server it got established, right? So but if it has to submit the rights to the master, then it can only establish that session with the master, right? Which means all client will have to inadvertently kind of establish a session with the master, which doesn't actually take place, right? So
And what happens if that server to which a particular client is connected to, the Zookeeper server, what if that server goes down?
yeah,
Would
so
that be automatically switched?
yes. So the client actually takes care of it. So we are the API level or at even the CA level, right? So we are not exposed to that directly. So what usually happens when that server goes down, right? So whoever with whom my current session is, the client usually doesn't immediately, like break down the session. So what it does is like it tries to because it knows the entire quorum, right? It knows the entire ensemble. It tries to communicate, right, with one of the other servers, right? And then let's say it establish the communication, right? So and then that all the information about that existing session, right? Like so the new server, the client kind of gives the information about what are all the outstanding watches that has to be handled by this new server who's going to take care of my session now, right? Like so, and then the new server kind of starts establishing those watches over there, and the client actually establishes it. So yeah, so there is a small switch over that actually happens when whoever I am right now connecting to, right? If he goes down, I contact one of the other ones, I establish a session, and then I give the set of outstanding things that the server should know about, right? Like in order to get the session, in order to recreate that session, right? Like all the outstanding watches and stuff like that. And I think probably there is also a little bit of session information stored permanently as part of by the first server, right, within Zookeeper itself. So it should probably be able to retrieve one set of information from there, but there is also some feeding information that it gets from the client itself directly, like with the watches and stuff. And then
And this
we
this would be supplied by the uh, clients, the CLI or the SDK. The client itself should not be dealing with this firsthand, right?
you mean the client itself should not be dealing with the
So the
uh,
way which so we were trying to use the CLI to do various things, right? Set
yeah,
the watches and things like that.
yeah,
Here the CLI is actually talking to the server, maintaining the session and
yes,
like reading those watches.
yeah.
So now for some reason the server goes down. As a client, we will not have to do anything. The CLI will take care of doing the switch.
Exactly, yes. We
Hmm.
won't actually the only time when we'll be notified, right, as an application who's using the CLI or who's using the API, the only
Hmm.
time that we will be notified is if for some reason, right, like I'm not able to communicate with the other servers, and I'm not able to establish that session, right? Like so,
Hmm.
then we'll actually be notified of the fact that the session got terminated.
Got it. And if the ensemble changes for some reason, if we want, I think removal is automatically detected. But if I want to add more servers, do I have to restart, or is there a way to
Yeah.
just say that, hey, add this is added to the
Yeah,
ensemble
so
now?
usually, right, that's a very unusual change to a Zookeeper cluster. Usually, Zookeeper
Hmm.
clusters, as I said, right, they exist in terms of 3 or 5, right? And I think most probably, I've seen installations of five Zookeeper nodes, right? Like, but they actually have a lot of. There's one thing that we didn't look at. I think they're called as observers, right? Like that actually don't take part in a quorum, but they simply learn the results of a quorum, and they also have the replicated state machine among themselves.
Hmm.
So like in order to support more throughput, you can actually have multiple of those observers, right? So but yeah, to answer your question, the normally the size doesn't change. And I think they brought in I don't remember the Zookeeper version, but they brought in a change for this dynamic reconfig and stuff like that, where
Hmm.
you can dynamically add a server. But like when I used this, I think in 2016, I don't think we had dynamic reconfig, or maybe it was the time when they were kind of developing it, or it was in the current beta version. So if we never had to change a Zookeeper ensemble. We always had a 3-node ensemble, and that's all we worked with. So, but I think yeah, because even the way in which, for example, when we start the server itself, we kind of hard code the Zookeeper ensemble in the server's config, right? So
Hmm.
the same happens even when you start the client, right? So usually, as far as I understand, it's a static information, and any dynamic changes probably have to be like you have to bring them down, and it's very rare they change
Yeah,
that ensemble.
makes sense. Cool. Thank you so much for answering all these questions so patiently. Really appreciate that.
No problem.
Yeah. Thank you, Johnny. It was a very nice session. Yeah.
No problem, sir. Thanks.
Yeah. So I think, shall I stop the recording?
Yeah, sure. Yeah, I think the one last thing that I wanted to mention was for the Zookeeper part 3, right? Like, so I think I kind of already mentioned this. So we'll have this probably not next week, but we'll wait until DDAA session that happens